So we have a definite integral here that we have to try to compute, and we have a hint telling us to try substituting e to the 2x plus e to the negative 2x. So we'll start off by doing that. U equals e to the 2x plus e to the negative 2x. So in this case, du would just be the derivative of this. So e to the 2x, the derivative of that is just e to the 2x, and the 2 comes down because of chain rule. And same thing for this, except it's a negative 2. So we get minus 2e to the negative 2x dx. Now, if we look at this, this is just our numerator, but multiplied by 2. So if we divide both sides here by 2, we get du over 2 equals e to the 2x minus e to the negative 2x dx. So this thing right over here can be substituted by du over 2. And we can plug that into our integral. So this can replace this. So if we do that, then what we get is the definite integral of, this is du over 2, and the denominator is just u, so it's 1 over u du over 2. And now, since we're taking the definite integral, we have to make sure that our lower and upper bounds of integration are consistent with our variable, which is u now. So if we plug in u into x, then we get e to the 0 plus e to the 0, so that's 1 plus 1. So our lower bound becomes 2. And if we take our upper bound, then what we get is e to the power of 2 plus e to the power of negative 2. So that's e squared plus 1 over e squared. So now if we integrate this, well, we know that the integral of 1 over u is just ln u. So we have 1/2 from the 2, and then we have ln of u. This is evaluated from e squared plus 1 over e squared and 2. And in this case, we don't have to put the absolute value signs there because we're evaluating it at positive values. So if we do evaluate this, then what we get is 1/2 ln of e squared plus 1 over e squared minus ln 2. So this is our final answer for this definite integral.